In this example, we have a circular wheel which is rolling without slipping to the right. We know that the center of the wheel O has a speed of 5 feet per second. That speed is decreasing at a rate of 3 feet per second squared. What we want to know is what is the acceleration of this point P in the circumference of the wheel when theta is 90 degrees. That is, when P is directly above O. First thing I'm going to do is draw a picture of the situation at the instant of interest. We got O here in the middle, of course. We're interested in the case when P is directly above O. I'm going to introduce this contact point C, probably the most critical point in our analysis, because that's the point where we're going to enforce the no slip case. And what I'm going to do first is deal with a relationship between O and C for velocity and also one for acceleration. Those 2 points are important because we know everything about O and we know a lot about C. Okay, so the first thing I'm going to do is say velocity of O is equal to velocity of C plus omega crossed R going from C to O. Now, what no slip means is that point C, the contact point, has the same motion in the x direction as the ground. Well, since the ground is fixed, its velocity is 0, therefore the velocity of the contact point is a 0. Omega, we don't know what that is. We do know it's about k, and we'll leave omega as an unknown. We're going to find that. The vector which goes from C to O is an rj. K cross j is a minus I, so this becomes a minus r omega I. VO, O is moving on a straight line, x direction, so that's VOI like this. So I can balance out the coefficients in front of I and see that VO is equal to minus R omega. So we see from here that omega is equal to minus VO R. VO is a positive 3, so this is 3 divided by 2. No, I'm sorry, that's not 3. It's a 5 divided by 2. So that's, of course, in radians per second. The negative sign is important because it tells us that the wheel is rotating in a clockwise sense. Why is that? Well, right up here when I wrote omega k, I made the assumption, without thinking about it, that it was rotating in the counterclockwise sense in the positive k, and I was wrong. The negative sign tells me that, so therefore it's in the clockwise sense. I do the same thing for acceleration. Acceleration of O is equal to acceleration of C plus alpha for the wheel, cross with the vector which goes from C to O, minus omega squared R C to O. This requires a little bit more thought. C is still a no-slip point, and as I said before, the motion of C in the x direction is the same as the ground. So the x component of acceleration for C is a 0. The y component may not be. In fact, it will not be. So all I can say is that ACX is 0. So all that I can say for sure is there's something in y. We don't know what it is. Alpha is an unknown. I'm going to assume it's plus k. Let the math tell us whether that's right or not. Going from C to O is an rj minus omega squared rj like this. Acceleration of O, well, O is moving on a straight line path in x. I'll put the correct sign on AO in just a bit, but that's just in the I. So whenever I do my cross product, I get minus R alpha, K cross J is a minus I. Get AC minus R omega squared in the J. So I have one vector equation, and that vector equation has 2 components, I, which says that AO is equal to minus R alpha. So therefore the alpha is equal to minus AO divided by R. So that's a minus, AO is a minus 3 divided by 2. So that ends up being a plus 1.5 radians per second squared. The plus sign, well, it just means that whenever I guessed positive K up here, I was right. And positive K means counterclockwise. The J component. The J component says that there's a 0 on the left-hand side. On the right-hand side, you got AC minus R omega squared. So I solve this, I see that AC is equal to R omega squared. The important thing on this is it's not equal to a 0. No slip does not say the y component of acceleration is 0. It only says that the x component is. Okay, great. So now we have alpha, we have omega, we can go straight to P. So AP is equal to, I'm going to use 0.0, AO plus alpha cross R. The equation looks a lot the same as we used before, but we're just going between different points. Like that. We know AO is minus 3i. That's given information. The alpha vector we saw was equal to 1.5k. The vector which goes from O to P, that's going to be in the positive j. The distance r is 2. Like that. Got omega squared 2j. So whenever I do my cross product of k with j, combine it with the other terms, I get minus 3. I get a k cross j, again we said was a minus I, so that's a minus 3 again. And the j component is going to be 2 times omega. Omega was equal to minus 5 halves. So that's a squared, and that's in the j. So in the end here we have minus 6i. We have a minus 25. That's 5 squared divided by 4 times 2. That's 25 over 2j. And that's in feet per second squared. So we see that the acceleration of p has a negative component in x. It has a negative component in j. It looks like the j component is 12.5, so it's about a little bit more than twice that it is for x. So here where we're asked to make a sketch, we see that if I draw this scale here as being like a minus 6, then twice that would be something like that. So the acceleration of point P would be looking like that. Because again, it has a negative x component of 6 and a negative y component of 25 over 2. Maybe not drawn very well to scale, but at least you get the idea. It's negative x and negative y. So what did we do here? First thing we did was went between O and C for both velocity and acceleration. The key part of this was no slip means no velocity for point C. No slip means no x component for acceleration of C. As we saw, it did have a y component. But once we had alpha and omega, then we went straight from O to P with our rigid body acceleration equation as shown here. We used the results for alpha and for omega, And that's the result that we got.